Welcome to Understand the Math. In this video, I'm going to introduce you to exponential functions, an incredibly important concept in mathematics. We'll explore what these powerful functions are, how they work, and what sets them apart from straight-line graphs that you might already be familiar with. We'll start with the very definition and general form of an exponential function. An exponential function looks like f of x is equal to a times b raised to the x power. A is a constant, and it's the initial amount or the y-intercept. It's where the function starts when x is equal to 0. B is also a constant, and it's super important. It's your exponential growth or decay factor, and it's also known as the base of the exponential function. This is the number that's being repeatedly multiplied. X is a variable, and it's the input or exponent. This is what makes it exponential. Now, there are two crucial rules for b. b has to be greater than 0, and b can't equal 1. The reason that b can't equal 1 is if it did, our f of x would just be a times 1 raised to the power of x, which is just a, and that's a constant. So it wouldn't be an exponential function. Let's now look at a simple example and see how this works. Our function is f of x is equal to 2 raised to the x power. To understand how this function works a little bit better, let's fill out this table. We're given values of x, and we want to find what the f of x values are. All we're going to do is plug x into our function 2 to the x. When x is 0, our f of x is 2 to the 0, which is 1. When x is 1, our f of x is 2 to the 1, which is 2. And then when x is 2, we have 2 squared, which is 4. When x is 3, we have 2 cubed, which is 8. And then lastly, when x is 4, we have 2 to the 4th, which is equal to 16. So that we can understand this visually, I've plotted these points on our graph. When x is 0, f of x is 1. And then when x is 1, f of x is 2. And then we go to 4, and then to 8, and then all the way up to 16. Notice that when our x value changes by 1 unit, our function gets multiplied by a factor of 2. You can see this in our graph. When our x value changes 1 unit at a time, our y value gets multiplied by a factor of 2. This is a hallmark of an exponential function. We have what we call a constant ratio of change. To truly appreciate what makes an exponential function unique, let's compare them to something you're probably already familiar with, linear functions. We're going to look at the linear function f of x is equal to 2 times x, and we're going to fill in our table just like we did for our exponential function. When x is 0, our f of x is 2 times 0, which is 0. When x is 1, we have 2 times 1, which is 2. When x is 2, we have 2 times 2, which is 4. We then have 2 times 3, which is 6. And then lastly, we have 2 times 4, which is equal to 8. I've put all of these points over here on our graph. When our x value changes by 1 unit, we're just adding 2 to our function. We call this a constant difference. The big takeaway from this is that exponential functions involve multiplication by a constant factor, called a constant ratio, and linear functions involve the addition of a constant amount, which is called a constant difference. This fundamental difference is why exponential functions can skyrocket so much faster than linear ones. Exponential functions can show two main behaviors, growth or decay. Let's first look at exponential growth. A function f of x is equal to a times b to the x grows exponentially when its base is bigger than 1. When the base b is bigger than 1, our function is increasing and it's concave up. Let's now look at the end behavior. As x gets really, really large, our function also gets really, really large, and we say that f of x goes to infinity as x goes to infinity. Let's now look at the other direction. As x gets really, really small and goes to minus infinity, our function is going to go to 0. It's never going to reach 0, it's just going to approach 0. Let's now talk about exponential decay. A function that exhibits exponential decay looks like f of x is equal to a times b to the x, but here our base b is between 0 and 1. A decaying exponential function decreases and it's concave up. Now let's look at its end behavior. As x gets really, really large, the opposite happens. Instead of going to infinity, it's going to go to 0. And then when x gets really, really small and goes to minus infinity, our function is going to go to infinity. Let's now look at some examples. We have the function f of x is equal to 4 raised to the x, and f of x is equal to 2 raised to the x. These are both functions that are increasing exponentially. Notice that the function 4 to the x is larger than the function 2 to the x. The reason for this is that the larger base produces a steeper curve. Let's now look at some decaying exponential functions. We have two functions, f of x is equal to 1/2 raised to the x, and then f of x is equal to 1/4 raised to the x. Here the opposite happens. A smaller base produces a steeper curve. Exponential functions are really important because they can be used to model countless phenomena in the real world. Here's some examples. Exponential functions can be used to model population growth. Whether it's bacteria in a petri dish or animals in a protected reserve, populations can grow exponentially under ideal conditions. Compound interest can also be expressed as an exponential function. This is how your money grows in a savings account or investment over time, with your interest earning interest. These functions are also used to model the spread of disease. Unfortunately, the initial rapid spread of viruses or infections often follows an exponential growth pattern. Exponential decay can be seen in the cooling of an object. When a hot object, such as this cup of hot chocolate, cools down in a cooler environment, its temperature decreases exponentially towards the ambient temperature. Understanding these functions helps us predict, analyze, and even manage these real-world situations. And that's your essential introduction to exponential functions. You now know their general form, what makes them tick, that constant multiplication factor, and how they differ from linear functions.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.